All right, we'll get started here, get rocking and rolling today. So we went through the first page yesterday, and so what we want to start looking at here is page 2 in terms of finding volumes of irregular figures. And in this next one right here, we're going to start talking about some boundaries within the coordinate plane, and then it's going to be like a cross-sectional shape that we're going to form like this. But guys, take a look at this shape right here that I put on the pencil. Can you guys see that right there? If I start rotating this around, can you kind of see the volume or the shape it's going to make if I start rotating this around like that?
It's a cylinder.
Kind of be like a cylinder, but it's not quite a cylinder, more like a cone, but the corners will be kind of rounded, won't they? Or the edges be rounded here. So can you kind of visualize? I'm trying fast. You see it?
Yeah.
Okay. Thought I was going to start a fire here for a second. Started smoking on me. Okay, so right here this says find the volume of the figure bounded by the region of the x and y axis. So two of our axes are always going to be the x and y axis. Well, I shouldn't say always, but at least in this example it's going to be. But guys, anytime you get stuff like this, the first thing I'm always going to ask you to do is to make a sketch of these. All right? You're always going to want to sketch these. Why does that do that? I don't want that. This computer's a little different compared to the other one.
You just get a new one or something?
Well, no, it is new, and I always have it over there to work with. The other one I have was purchased with funds from a teaching in 2017, and this had some money I had from a grant. I got a new laptop that I've always used to, but track and field uses that computer to do timing system. In order to do timing system, they got to upload all the stuff into that computer. So Mr. Bruns needs that to get ready for tomorrow's meeting, so I had to switch over today. All right, guys, so you're always going to make a sketch. So the first thing that we have here is the x and the y-axis. Okay, you with me on that? So I'm just going to sketch an x-axis and y-axis like this first. Okay? It says it's also bounded by the line, what's this say, kids? X equals 4. Okay, so that would just be like going over here. Say, well, this is my 4, and that would be a vertical line at 4. Okay, and then the next one is the equation y equals what?
X squared plus 3.
Okay, so it looks like we're going from left to right. It looks like we're going from 0 up to 4. So if I plug 0 into this function, what would 0 squared plus 3 make?
3.
So it might start up here at about 3.
It'd be from a polynomial or whatever.
Yeah, it'd be a polynomial. Actually, it'd be a quadratic, so it's going to be kind of curved, isn't it?
Yeah.
Okay. If I plug 4 in, what's this value up here?
It's gonna be 4.
Okay, what's 4 squared when I plug that in?
16.
16 plus 3 more would make a y value up here of what? Okay, and you guys agree that this would be a quadratic. This is kind of the shape we're going to make right here to that point, isn't it? And conveniently, isn't this kind of what it makes right here? Now, it says we're going to rotate this around the what, kids? Okay. I'm going to give you a big concept right here. Anytime they tell you what axis to rotate around, you will make your slices
The opposite.
perpendicular to that axis. So here's my slice. Now keep in mind the width of this slice, really big or really small? Really small. So we're talking about this slice right here. I'm going to color that in. Okay, now this slice right here, anytime you have a slice where you're talking about rotation, I'm going to make a note right here. Slices should be perpendicular, and the perpendicular symbol is just an upside down T, perpendicular to the axis of rotation. So in this problem right here, which axis of rotation are they suggesting again, kids? It says rotate around the what?
X-axis.
Well, isn't x-axis the horizontal axis?
It is.
So if I'm gonna have rotations around the x-axis, my slices better be perpendicular to the x-axis, all right? Now, when we talk about rotating stuff, we're gonna get a slice, my friends. And I told you that if you can come up with a function for your slices, this becomes a pretty easy problem. So, here's what we're after here today, kids. First of all, this little distance right here, is that a change in x or a change in y? Okay, so I'm going to call this delta x right down here. Delta x meaning that this is the limit as x approaches what value for thickness? 0. We're going to have a bunch of little cylinders that are stacked next to each other, or that rotate around this x-axis that form the volume of this shape, kind of like what we saw when we were rotating that figure on the pencil. So, guys, I told you yesterday that when you determine your slice, which variable is going to kind of drive everything right here? Okay, the x is going to drive everything. We need to write stuff in respect to x. Now, kids, how about my radius right here, kids? Is this a vertical distance or horizontal distance for the radius when I start rotating? So I'm going to call this distance y. Is that okay? Make sense to you there? All right. So here we go. We're going to write a function for the volume of one slice. And the volume of our one slice, guys, you agree that this is a cylinder, right?
In a way, yeah.
What's that?
In a way, yes.
It's going to be a cylinder with very minimal height to it, right? Okay, it's going to be like a flat circle. Okay, so this is going to equal. You guys recall the formula for the volume of a cylinder?
Something with pi in it.
Pi times the
Radius squared
radius squared times the
height.
height. Okay, so my volume of the slice becomes the following.
We're gonna have to remember that formula when we take the test.
Well, if you don't remember it, Google will remember it. Sound good?
Yeah.
Okay. And I honestly don't think there'll be a test here by the time you guys are ready to be done here.
Or a quiz even though.
Yeah, I'm hoping to get you through 4 sections and be in good shape that way.
Can Kate also not take the test?
I think you'll be okay, Kate. I'm not worried about it. Okay. All right, here we go. Guys, let's fill this in. This is going to become pi. Okay, what value in this diagram really is my radius then? Is it the y or the delta x?
Delta x. Well, half delta x.
Hey, I'll be careful now, okay? Because if you rotate this, these
Oh,
are...
why would?
Yep, and let me grab a piece of this back here. Isn't this cylinder going to kind of be... If you can kind of visualize this, isn't this the cylinder we're kind of... I mean, imagine the height of this being 0. Aren't you kind of looking at the cylinder like this right here? So the radius for you guys is really from this axis of rotation, which is right here, right? That would be from the axis of rotation up to here, wouldn't it? So your radius is really what variable in this drawing? It's really y, isn't it? Okay. So, this becomes pi times, to replace the radius, we've got y squared. And then really what's the height here of that cylinder? Yeah, it's just that delta x, right? Okay. Now, pi is okay since that's a constant. Delta x is going to be the variable we want to get everything with respect to. Y is not some constant. It's not saying that y is some number. We're saying y is the radius. So, kids, what we need to do is get rid of that variable y and write it with respect to what? Okay. Now, the nice thing about these problems is this. We already know what y is really equal to in terms of x.
X squared.
Yep, they gave it to us right here. They said y is equal to what right here, kids? So what could I really replace the y with?
X squared plus.
Okay, so my function here for one slice becomes the following. It becomes height.
Hi.
Our volume for the slice here, all in terms of x, is equal to pi times, what are you going to replace the y with? We're on the notes there, Belle, so if you want to grab them and,
X squared plus 3.
yep. Actually, I can take a picture of this and then get it down that way, okay?
Sound.
So y is replaced with x squared plus 3, isn't it? Okay, but that x squared plus 3, that quantity would be taken to which power?
Second.
Yep. Times the height delta x. Kids, have we have we, how do I want to say this? Have we written a function for the value of our slice, all in terms of x right now? Is that a good thing or bad thing? That's a good thing, because now you can write your function for the total. Our total now becomes the following, kids. Our total volume of this figure that we're about to find the volume for becomes a definite integral, okay? Well, guys, everything's written with respect to x, so the limits on the x-axis are what I'm looking for. So what are my limits on the x-axis according to this drawing? So it's going to become the definite integral from 0 to 4 of pi times x squared plus 3, all to the second power. Since we're talking about the summation of all slices right there, delta x will become dx with respect to all x within that definite integral. And guess what, kids? I'm not going to make you find an antiderivative this time because we have numbers in here to work with, so where are we going now?
Decimals.
We're going to decimals, and we're going to say, help me find the definite integral value here. So let's do that here real quickly. All right, friends. So, decimals. All right, so INT, what are my limits, kids? Zero to 4, is that right?
Yep.
Of pi times x to the second plus 3, all to what power? D what? What do we have for a value? And I'd say 2 places is pretty darn good there, kids, but what do we have for a value now?
1,158.60.
So kind of what we're talking about is this, kids. We have these little slices that are rotating like this right here, rotating around, but they're little slices within this shape running up and down. And if you can imagine me, once I've got that bounded, just rotating around the x-axis like this, you kind of see the shape that's formed here when I go quickly with it. It's kind of, I don't know how to, if it was this way, it'd be kind of like a bowl, wouldn't it? Bowl shape almost, right? Or we could rotate it this way. And we're going to start rotating different directions to see how it changes values in terms of the shape we get. But guys, in the end, what do we get for a volume rotating around the x-axis with those bounded, or with that bounded region?
1,158.60.
Yep. 6.2 you said?
Yeah.
And then since we're talking volume, we should probably make this what type of a unit?
Cubic.
I'm just gonna put UN cubed like that for units cubed, okay? Now guys, here's the deal. I like these problems because do they require a ton of work? Compared to what we looked at yesterday, how is this?
So
Awesome.
easy.
This is much better, right? Compared to the things that we looked at yesterday, this definitely much better, okay? All right, let's try another example here. I don't know.
Flip the page or go to that example.
I'm gonna make one up here,
Here, make one up.
okay? Val, did you get a picture of all that?
I'll take a picture of Kate's.
All right,
I have half of it already done.
well, I'll wait for you then. Sound good?
Oh, okay.
'Cause I need another drink of coffee. I wanna look ahead too. Who's got notes I can look at real quick? Can I see yours quick?
Carson, do you want another dog? Because I have one that is up for adoption after this morning.
Why, what happened?
Well, I was at my dad's house and my mom called me and she's like, he's been hiding under my bed since 6 a.m.
Oh,
Because
because
if
of
he
the
hides
storm?
Yeah, and because if he hides under the bed, he doesn't get put in his kennel. So we like can't get under there to get him. So she's like, will you go home and see if you can get him to go outside? And I was like, yeah. So I get home, I chased him around the house for 10 minutes. I got him outside. He got out of the fence. I chased him around the neighborhood for 10 minutes in the rain. I was angry. And then he like came back inside and just laid on my bed.
What kind of dog is he?
He's a Shih Tzu. A Shih Tzu poodle. He's like 11 pounds.
Yeah, he'd fit in well with my other 2 dogs.
Yeah, that's what I'm saying.
I'll take him.
Okay.
What's his
perfect.
name?
Oliver,
Yeah.
he sleeps 90% of the time, it's just when he's not sleeping, that's the problem.
So he's like a A-minus dog.
Yeah, basically.
Alright, I'll take it.
Oh,
Actually, guys, I'm gonna move to the next page. We're just gonna go right to the next page with this. You got it, Bill?
yes.
Okay, let's do the next page right here. This is gonna get a little more difficult here. Okay? Now, one thing I wanna point out right here is this. This is not always gonna happen to you guys, but guys, what axis did we rotate around? The x-axis right here. And wasn't the x-axis also one of our boundary lines for this region right here? Okay, it was. It was the boundary line for that region. Okay, so sometimes a boundary line will be a border for your region. There's gonna be other times when the axis of rotation is not a boundary line for your region, and we'll look at how to handle that here probably on the next page. Okay? All right, but ones that have the boundary line like the x-axis as the axis of rotation, if your axis of rotation is one of the boundary lines, this turns out to be a pretty nice little thing. Okay, works well. However, we wouldn't want it to be that easy all the time. Okay, this one here says find the volume of a figure bounded by what, kids? X and Y axis. Your function is 2x squared plus x plus 3, and rotated around the x-axis. So I'm going to have you try this one on your own. Let's get the sketch of this first, okay? So the x and y axis are boundaries, right? Okay, what's the other one? X equals 5, so that looks like this, doesn't it? Put a 0 here. Okay. If I plug 0 into this, what would you have as an ending value? This is kind of similar to the other one, isn't it? Okay, if you had, oh boy. If you had 5 in there, what would that put you up at up here? 58, right. And it's a quadratic, so isn't this gonna curve again like this? All agree with that again?
Yeah.
Well, it's the same problem, isn't it? Okay, what are we rotating around? The x-axis. Okay, I'm gonna get goofy with you, and I'm gonna go back to that example here in a second since we're getting good at this. But I'm gonna go ahead here and say, ooh, what would happen if we rotated not around the x-axis, but if we rotated around the what? Show you the y-axis here in a little bit. So wouldn't this be a slice right here, kids? And we'll fill that in. It's about like this. Okay. What's the width of your slice?
Delta X.
Gets you all choked up, doesn't it?
It does. It just hits me right where it hurts.
So this is delta x down here, right? Okay, isn't your radius gonna be y again, kids? So the volume of one slice. Cylinder again, right?
Yes.
It'll equal pi times y squared times delta x, where y represents your radius and delta x represents the height of that cylinder. But since things are in terms of delta x, we should probably get y in terms of x. And what is y equal to, kids?
2x squared.
So the volume of one slice will equal pi times 2x to the second plus x plus 3. That's really the y value, but I want y to what power? Second times the height, which would be delta x. And then the question becomes this: have I written the volume of one of those slices all in terms of the variable that we desire, in this case x? So how are you going to turn this into a total? What are your limits on the x-axis for this?
0 to 5.
Total becomes definite integral then from 0 to 5 of pi times 2x to the second plus x plus 3, all to what power?
1 to the second.
And then all the delta x's become the summation of every one of those, so we put a all with respect to x there. Where am I going after that? Remember how much work we had yesterday?
It's about half of it.
It ain't even close to half, I don't think. I'd say it's about 1 over pi value of it.
Half the thought at least.
Yeah. Let's go to the calculator. You're gonna tell me what to type in, kids. We're replacing just the radius, right? Actually, I almost have. 0 to 5 on my limits. Good catch. So it's 2x squared plus, I can't remember, kids.
X.
And is it plus 3 after that?
Yeah.
Okay, so do I have this typed in there correctly, guys? Okay, so what's the volume of that shape when we rotate it around the x-axis? 11,000.
Is it 896?
896, yep. Let's go 1.6 on that, all right? I don't know, I think these are kind of fun.
They're like satisfying once you know how to do it.
It is, isn't it? All right, you guys got your value down there? All right, so you tell me, what did we get for a total then?
11,896.
.16, was it?
Yeah.
Okay, there it is, 11,896.16 cubic units there. Nice. Now, I know you're sitting there, you're saying, come on, Parson, they can't all be this easy, right? Good. It's because you guys want a challenge.
Did we?
Remember, now, just like the last example, was the boundary line, I should say it this way, was one of the boundary lines an axis of rotation? Yep, the x-axis bounded this, the x-axis was also a rotation axis for us. So, I wanna know what happens when I don't have an axis of rotation as a boundary line, okay? I think I'm gonna start with decimals on this one to kind of see what this looks like here. So, let's head down to this next example. I want you to put a star by this example, okay? All right, this tells us the following. We're gonna sketch this a little bit. Decimals might help you see the shape first and then allow you to make a better sketch here in a second. So let's do this. I'm gonna have you guys tell me what the regions are. Okay, so I'm gonna go to decimals. You tell me what these bounds are and what the axis of rotation is. And we'll kind of talk about what we're doing here, okay? So, this gets pretty interesting. Okay, what are our boundary lines, for example, that we're looking at right now?
X equals 1.
X equals 1. So won't that just be a vertical line at 1, kids? Okay. What's the next one?
X equals 5.
X equals 5. Okay.
And then y equals x squared. Plus 3x plus 5.
So x squared plus 3x plus 5.
Yep. Okay, and then y equals 2x plus 5.
Oh my gosh.
And then you rotate around y equals -2.
Okay. I'm going to zoom out here a little bit. Actually, I'm going to make this fit a little bit better, so give me a second. We have a mess here. Do you guys agree?
Yeah.
Okay, you guys kind of see this shape right in here. There's the vertical lines. There's this line right here. And then here's your 2x, I'm sorry, your x squared plus 3x plus 5 and your 2x plus 5. So guys, real quickly, if I did this, and you know what I'm gonna do? What's the axis of rotation then again? Y equals what?
-2.
Okay. You're not gonna like this one. I'm just gonna be honest with you on this one, okay? I'm gonna type in y equals -2.
Oh.
Okay, the dotted line's your axis of rotation, all right?
It's gonna be like a bunk.
It's gonna be a weird thing, but here's the deal. The shape that we're really working with bounded by the black line and the purple line and then the two vertical lines. So I'm gonna make the, I'm gonna go ahead and kind of highlight this, but here's the deal. We'll talk about this in a second. Now let me highlight this whole thing with my tools. Okay, here's what I want to get at. Where did I set my marker? There it is. Guys, this region that I'm about to outline right here, this is the region. You see that piece right there? We're gonna go ahead and take that region and probably do what with it, kiddos? Gonna kind of rotate that thing, aren't we? It's gonna rotate it around, what here, kids? Y equals -2. Now, when I start rotating that piece, is that piece gonna have, is that piece gonna have, an axis of rotation has a boundary? Okay. We start rotating this thing isn't even touching. When I start rotating this, what's gonna be true about the very middle of this shape when I start rotating it? It's gonna be hollow in there, isn't it? Okay. So here's how we start working on this right here. We start looking at slices in two different ways, okay? First of all, volumes of hollowed out shapes like this, okay? It's kind of like saying, start with it as if it was a whole shape. So pretend this hole isn't in this shape right here, okay? If I can find the volume of the whole, if it was a whole piece first, then can I subtract the volume out of the hollow part to get a total volume that's left over? Makes sense to you?
Yeah.
So when you have something like this, where you have an axis of rotation that does not act as a boundary line, typically you get something that's hollowed or bowled out. I say like carved out in there sometimes, there's a bowl to it. So here's how this works. I'm gonna draw on this and then we'll come back and make the sketch. So right here, kids, we start first of all pretending that this was a whole piece. So forget this bottom green line right here, like right in, whoops, I didn't wanna do that. Forget this bottom green line right here. We start talking about how do you put a slice in here? Well, I'm gonna put a slice in here quickly for an outside one, okay? What we do when we have hollow shapes is we start talking about slices and finding volumes by taking the volume of outside slices minus the volume of the inside slices, where the volume of the inside slices represents like the part you're gonna hollow out or take out of it. So here's how this works, okay? This could be one slice, maybe down to the x-axis. But guys, is that going to the outside part of it when we rotate it or to the inside part? Okay. If I rotated this, wouldn't this part be right here? Would this be inside or outside part here? Outside part. And then here would be a slice for the inside part of this, okay? All right. So what we do is we figure a whole volume based on outside. We figure a whole volume based on what's on the inside. And then the total volume left over is just the outside volume minus the what? The inside volume. Okay, so things get a little goofy here. Okay? I'm going to do the best to replicate this here in a second on a drawing. Is that okay with you guys? In fact, I wonder if I can do this. Let's see how smart Parson is today. I don't know if this is going to work. Nope, gosh darn it. Is there a way to take a screenshot on these computers?
Is that one that Chromebooks?
Yeah.
Control Shift, and there should be like a couple window tabs that you click.
I have like a window tabby thing up here, Control Shift. just hit control or function. And decimals is locked
Click
down.
on the.
It's okay, I'll just sketch it. It's all good, trust
I
me.
was gonna say, if you just click on the search tab on it below, you probably search up like snippet tool.
That's what I'm gonna do right here. Is that okay with you guys? Now, can I paste in here?
Should be easy.
Can I hit Control V?
Yeah.
Whoa, will you looky there? I learned something today. Life is good. Sorry guys, I get a little goofy.
You get excited when you learn.
Yeah. Okay. Guys, what I might tell you to do is this. This line right here, we're gonna label some stuff. Now here's the deal, I think I'm gonna run into problems now though. This is the line x equals 2, right? Right here, so this value is at 2 down here, right? Did it say x equal 5 also? No, it's 1, isn't it? So this is x equals 1 right here, this vertical line, right? So this 2 down here should be what value? Agree 1, right there? Okay, this is at 5, isn't it? Okay. All right, this equation for this line was, what was it, y equal 2x plus 5? And this equation right here was y equal x squared plus 3x plus 5 here. Okay. All right, so we all agree right here. You guys tell me if you agree here or not. Let me do this quickly. Maybe I can cheat this a little bit. Hang on a second. Oh, try this parson. Okay, so you it's not a perfect fit in there, but you guys gonna get the idea of the shape that we're gonna get in there? Okay, here's what we're doing, kids. Now you gotta be careful on this. We're gonna start with our outside slice first. Is that okay with you guys?
Yes.
So let's start with an outside slice. So we're going from this line of rotation at y equals -2. Okay, we gotta be careful on this. The radius to this outside slice, first of all, do we all agree that this is a delta x down here for that slice?
Yeah.
Okay, so let's color that slice in. Okay, so this slice gets colored in here. But here's the deal. We talked about this, first of all, is this a y distance or an x distance going up there for that outside slice?
Why?
It's a y, but it's not going from 0, it's going from what value? So it would really have to be y plus, if we started at the x-axis, we could say, well, it's just up there a distance y. But it's really a distance y plus how much more here, kids? This outside radius that we talk about, this outside radius right here, my friends, this outside radius is really going to have a radius of y plus how much more? Okay, everybody see what I'm saying there? If your axis of rotation isn't the x-axis or y-axis, you've got to consider how far your axis of rotation is away from something like that, okay? So let's come up with a formula for the outside slice. The outside slice would be pi times, what would the radius be here then, kids? Y plus 2, all to what power? Times delta x, right? Okay, so x is the variable I'm really concerned about. For that outside slice, what could I replace the y with for that outside slice? Isn't this your outside boundary right here?
X
Came from that function right there, x squared plus 3x plus 5. So our outside slice, kids, is going to be pi times. Okay, guys, the plus 2 and the plus 5, when I put that plus 5 in here as y, what's the plus 5 and the plus 2 going to combine to?
7.
Yep, so this is going to be x squared plus 3x plus 7 delta x. Okay. Oh, Maddie, good catch again. You're on top of the game today. I love it. Have I got it right now, kiddos?
Yeah.
Okay. Now guess what we're going to do? Same thing for an inside slice, right? So let me draw this box here quickly. I'm going to have a box that goes up to here. We're going to take this volume out of the whole volume. If it was solid, then we'll take this out. So right here, I want to take that slice out. So talk to me about this. Guys, again, won't this radius right here for this boundary line be y plus 2 again? But what's going to replace the y?
X squared plus
Okay, for this boundary line, y is equal to what?
oh, 2x plus
2x plus 5. So this is really going to be a distance of 2x plus 7, isn't it? Okay, so let's do the inside slice here. Okay. Oh, this is so cool. Okay, so I'm going to do the same thing. For this inside slice, we would have pi times y plus 2 squared delta x again. But just like everything else, if x is driving this problem right there, I don't want the y in there. So on an inside boundary line, that's defined as 2x plus 5. What are you going to replace y with right there? So that quantity y plus 2 is going to turn into what's the 2x plus 5 plus 2 going to make?
7.
Okay, and then here's where the fun begins, kids. Once you get that far, this simply becomes the following, okay? The total is going to be the outside volume minus the inside volume, and the part that's left is going to be the shaded region rotated around the line of, or axis of rotation, y equals -2. Okay, so here's what my total is going to look like. I'm going to write the integral. Guys, as we're working with delta x, we need to look at my limits from left to right. So what was the left boundary line?
1.
What was the right boundary line?
5.
So it's the integral from 1 up to 5 of, okay, we're going to go outside slice. So pi times x squared plus 3x plus, what was it, 7?
Squared.
Minus the inside slice, which is pi times 2x plus 7 squared, all with respect to x. Okay? Now, if I told you find the antiderivative and use fundamental theorem, I think that you guys would leave in mass numbers. Probably leave before the 15 or 14 days that you have left, seniors.
That's crazy.
Where are we going with this?
Desmos.
Okay.
Disney World.
Yeah, that'd be a good idea too. Okay. So help me out here. I'm going to go to Desmos. And let me clear this drawing. All right, we are going to integrate from, what were my limits again, kids?
1 to 5.
Okay, I know it starts out pi, whoops. Pi times, okay, I can't remember, x to the second
Plus 3x. Plus 7.
minus pi times, what was it again, 2
X plus 7.
squared.
Yep.
Okay, now, it's not kicking a value out, is it? So what might I have to put around all of these? Yeah. Oh gosh, dang it. Okay, phew. Thank God for Control Z, right? Appelschog. There we go. So sometimes if you don't get a value to kick out, you may have to put some parentheses around the whole thing before the BX, but what do we get for a volume there, guys, with inside-outside stuff? 7,898.38. 7,898.38 units. Very good, Grant. 7,898.38 cubic units. You guys got your number down?
Yeah.
So right down here, what did we say the total was?
7,898.38 cubic units.
0.38?
Yeah.
Oop. There it is.
It's beautiful.
I love this stuff. It's so cool. Okay? It's like, ooh, this thing has a volume to it. What is it? Look, I have no idea because there's no formula for it anymore. A shape like that, would there be a formula for it? Have no idea what formulas, okay? So this is how we do it. And this is how all the formulas for like the regular pyramids or regular cones came up, this idea of slicing, okay? Kids, I'm gonna stop there today. We'll look at one more example tomorrow. I'll get you going on a quick quiz and some problems tomorrow in class, but what questions have you got for me right now?